There is a jar of Martian dirt sitting on the surface of Mars right now. Actually, it is not just one jar. It is dozens of sealed titanium tubes, carefully packed with ancient Martian rock and soil, some of the most scientifically valuable material ever collected by human hands, waiting to be picked up and brought back to Earth. Scientists around the world are practically vibrating with anticipation over what those samples might contain. Evidence of ancient life, clues about how planets form, answers to some of the oldest questions human beings have ever asked about our place in the universe. And those tubes have been sitting there, waiting, for years. And based on the latest information we have, they are going to keep sitting there for a very long time to come. If you have been following space exploration for any length of time, you have probably heard about the Mars Sample Return Mission. It is one of the most ambitious, most complicated, and most expensive space missions ever conceived by NASA and the European Space Agency. The plan was always straightforward in concept, even if it was never straightforward in execution. Send a rover to Mars, collect samples, and then send another mission to go pick them up and bring them home. Simple, right? Except that nothing about this mission has gone according to plan. Not the schedule, not the budget, and definitely not the politics. And the latest budget documents to come out of NASA are revealing something that a lot of people in the space community suspected, but nobody wanted to say out loud. This mission is in serious trouble. So if you want to understand what is actually happening here, what these documents say, why this keeps getting delayed, what is at stake, and what the future of Mars exploration might actually look like, stick around. And if you are the kind of person who gets genuinely excited about this stuff, who stays up reading about space missions and wondering what is out there, then you should subscribe right now, because this is exactly the kind of content we live for here. Let us start at the very beginning, because the story of Mars sample return is longer and stranger than most people realize. The idea of bringing back pieces of Mars to Earth is not new. Scientists have wanted to do this for decades. Even before we had sent a rover to Mars, researchers were arguing that the single most important thing we could do to understand that planet was to get actual physical samples into a laboratory on Earth. And the reason is simple but profound. The instruments you can fit on a rover, no matter how sophisticated, are nothing compared to the full arsenal of scientific equipment available in a modern laboratory. On Earth, scientists can run tests that would fill entire buildings' worth of machinery. They can expose samples to conditions that would be impossible to replicate in a spacecraft. They can study the same piece of rock for years, or even decades, passing it between labs and running new experiments as new technologies emerge. The history of lunar science proves this point. We have been studying the Apollo moon rocks for over 50 years, and we are still learning new things from them. Imagine what we could do with rocks from Mars. The push for a Mars sample return mission gained serious momentum in the early 2000s after the Mars exploration rovers, Spirit and Opportunity, started sending back data suggesting that Mars had once been a wet planet. That liquid water had flowed across its surface. That conditions had once existed that could, in theory, have supported life. That revelation changed everything. Because if Mars was once habitable, then the question of whether it was ever actually inhabited became one of the most important questions in science. And the only real way to answer it, scientists argued, was to bring back rocks from the right places on Mars and look for biological signatures in an Earth laboratory. But designing a mission to bring back Martian samples is genuinely one of the hardest things humanity has ever tried to do. It requires not one spacecraft, but a whole fleet of them working together across hundreds of millions of kilometers of space. You need a rover that can collect samples. You need a lander that can descend to the surface of Mars, receive those samples from the rover, and then launch a rocket from the surface of Mars into orbit. That has never been done before. Launching a rocket from another planet's surface. Then you need an orbiting spacecraft that can capture that rocket in orbit around Mars, transfer the samples into a return capsule, and then send everything back toward Earth. And then you need a system to safely bring that capsule down to Earth without it burning up or crashing, while also making sure that if the capsule does have a problem and lands somewhere unexpected, you do not accidentally contaminate Earth's biosphere with Martian material. Every single one of those steps is a major engineering challenge on its own. String them all together and you have something that has no precedent in the history of spaceflight. Now here is where the story of the Perseverance rover comes in, because Perseverance is the piece of this puzzle that is actually working. It launched in July 2020 and landed in Jezero Crater on February 18, 2021. Jezero Crater is a very specific and very intentional choice of landing site. About 3.5 billion years ago, Jezero was a lake. Water flowed in through a river delta, filled the crater, and then eventually dried up. And wherever you have ancient standing water on Earth, you tend to find life. Microbes, bacteria, organisms that leave behind chemical traces, and sometimes physical structures in the rock. The ancient delta and lakebed at Jezero are exactly the kinds of geological environments where, if life ever existed on Mars, it would have left evidence behind. Perseverance has been doing extraordinary work. The rover has driven across the crater floor, up onto the ancient delta, and collected samples from geological formations that scientists are genuinely excited about. As of the time this script was written, Perseverance has collected over 20 sealed sample tubes containing Martian rock, regolith, and even Martian atmosphere. Some of these samples come from ancient igneous rocks, which are useful for dating the geological history of Mars. Others come from the sedimentary deposits of the ancient delta, which are the ones that have scientists most excited about the possibility of preserved biosignatures. The rover has deposited a collection of backup sample tubes on the surface at a location called Three Forks, just in case something happens to Perseverance itself, and the samples need to be retrieved without the rover's help. The samples are there. They exist. They are ready to be picked up. The problem is that nobody is coming to pick them up anytime soon. Here is the timeline of delays, because it is worth walking through this carefully to understand just how dramatically this mission has slipped. In the early planning stages around 2018 and 2019, the rough target for a Mars sample return mission was the early 2030s. That seemed ambitious but achievable. Then, as NASA and the European Space Agency began working on the actual mission architecture in more detail, the complexity of what was required started driving costs and timelines upward. By 2022, the official target for returning samples to Earth had shifted to 2033. Already a few years off the original vision, but still within a reasonable window. NASA was committing to the mission, funding was being allocated, contracts were being awarded to companies like Northrop Grumman and Airbus, and the project was moving forward. Then in 2023, things started falling apart in a very public way. An independent review board that NASA commissioned to evaluate the Mars Sample Return Program released a report that was, to put it mildly, alarming. The board found that the mission architecture was not technically ready, that the cost estimates were wildly optimistic, and that the projected timeline was essentially impossible. The board estimated that the true cost of the mission as planned could reach somewhere between $8 billion and $10 billion, which was roughly double or even triple what had been previously communicated to Congress and the public. And the earliest realistic date for sample return, the board said, was somewhere between 2037 and 2039, maybe later. That report landed like a bomb in the space community. $10 billion for a single Mars mission was a number that nobody in Washington was going to easily sign off on, especially with NASA already juggling the Artemis lunar program, the James Webb Space Telescope's ongoing operations, the Roman Space Telescope in development, and dozens of other science missions. Something had to give. NASA's response was to essentially pause the mission and go back to the drawing board. They put out a call for new ideas, new mission architectures, new approaches that could bring the cost and timeline under control. Multiple aerospace companies and international partners submitted proposals. NASA began evaluating those alternatives. And all of that takes time, more time, another delay. Now we get to the really current part of the story, and the part that the latest budget documents are revealing in uncomfortable detail. The budget documents in question are part of NASA's fiscal year spending requests and the associated congressional justification materials. These documents are dense and technical, and most people never read them, but they contain the actual numbers and language that reveal what NASA really thinks about this mission, as opposed to what they say in press releases. And what these documents reveal is a picture that is significantly more uncertain than the public-facing narrative has suggested. The latest documents show that NASA has been forced to dramatically reduce spending on Mars sample return in the near term. The funding profile that had been established for the mission has been cut back, with resources being redirected toward what NASA is calling a more sustainable approach. But here is what that language actually means in practice. It means that the mission does not currently have a fully funded, fully defined architecture. The specific design for how the samples are going to be retrieved and returned to Earth has not been finalized. Contracts for the major mission components are in various states of limbo, and the target date for returning samples to Earth has now slipped, depending on which scenario you look at, to somewhere between 2035 and 2040. And even those dates come with significant asterisks and caveats. The documents also reveal something important about international partnership. The European Space Agency has been a critical partner in Mars sample return. ESA was responsible for developing the Earth Return Orbiter, the spacecraft that would fly to Mars, capture the sample container launched from the surface, and bring it back toward Earth. ESA has been doing genuine work on this. Hardware development has been underway. But the uncertainty on the NASA side has created complications on the ESA side as well, because partnership agreements are built on shared timelines and shared commitments, and when one partner starts shifting dates and budgets around, it creates ripple effects that are difficult to manage. There is also the question of what happens to Perseverance while all of this is being sorted out. The rover was designed to operate for a primary mission of 1 Mars year, which is about 687 Earth days. But like all of NASA's Mars rovers, Perseverance has continued operating well beyond its primary mission. As of now, the rover is in excellent health and continues to do valuable science. But no spacecraft lasts forever. The solar panels degrade, components wear out. The harsh Martian environment takes its toll over time. Spirit and Opportunity both lasted far longer than anyone expected, but they did eventually die. Curiosity is still going, but it is operating with reduced capabilities compared to its prime mission years. Perseverance will eventually face the same reality. And here is the uncomfortable truth that nobody in the official program is eager to say out loud. If Perseverance fails before a sample retrieval mission can reach Mars, NASA does have that backup cache of sample tubes deposited on the surface, so the samples themselves would not necessarily be lost. But the ability to continue collecting new samples from new locations, to add to the collection, to respond to new discoveries, that would be gone. And if something were to happen that damaged or buried the surface cache, the entire program's scientific return would be in jeopardy. Now let us talk about why this keeps happening. Why does this mission keep slipping? Because it is not just one thing. It is a combination of factors that have been building on each other for years, and understanding them helps you understand not just this mission, but the broader challenges facing deep space exploration. The first factor is genuine technical difficulty. Mars sample return is, as we discussed, one of the most complicated missions ever attempted. Launching a rocket from the surface of another planet has never been done. The Mars Ascent Vehicle, the rocket that would lift the sample container from the surface up into Mars orbit, is a significant engineering challenge. It needs to be lightweight enough to be landed on Mars, robust enough to survive the landing and the Martian environment, and powerful enough to actually get off the surface and into orbit. All of these requirements pull in different directions. Making it lighter tends to make it less robust. Making it more robust tends to make it heavier. These are not insurmountable problems, but they take time and money to solve properly. And when budget pressures cause teams to be reduced or timelines to compress, the engineering work gets harder, not easier. The sample capture mechanism is another challenge. The Earth Return Orbiter needs to find a container roughly the size of a basketball tumbling through Mars orbit, match its velocity, physically grab it, and secure it without damaging the samples inside. The orbital rendezvous problem alone has required years of study and simulation. Getting it right is critical, because if the capture fails, you have lost everything. The sample containment and biohazard protocols are a third area of genuine complexity. Mars sample return is classified as a restricted Earth return mission by planetary protection authorities. That means that unlike materials brought back from the moon, Martian samples are required to be handled as if they might contain living organisms, because we genuinely do not know whether they do or not, and the consequences of getting that wrong are potentially severe. Handling the samples requires a level of containment that rivals Biosafety Level 4 facilities, the highest containment level used for the most dangerous pathogens on Earth. Building the receiving facility, the sample receiving facility that will house and study the returned samples, is itself a major project that requires years of planning and construction. That facility does not fully exist yet. It needs to be built and certified before the samples even arrive. The second major factor is the cost problem, and this is where the political and institutional dynamics really start to matter. NASA operates within a federal budget that is set by Congress. The agency cannot simply decide to spend more money on something it considers important. It has to request funds, justify those requests in excruciating detail, and then accept whatever Congress decides to appropriate. And Congress has shown, repeatedly, that it is willing to fund Mars exploration in general, but gets very nervous when the price tag for a single mission starts climbing toward numbers that sound more like military procurement programs than science projects. When the Independent Review Board came out with that $8 to $10 billion estimate in 2023, it essentially guaranteed a political crisis, because those numbers were not consistent with what NASA had been telling congressional appropriators. There is a pattern in large NASA missions, and some critics have called it the foot-in-the-door strategy. A mission gets approved based on early cost estimates that are optimistic because optimistic estimates are easier to get approved. Then, as the mission matures and the true costs become clearer, the program comes back asking for more money. By that point, NASA has argued, so much has already been invested that canceling the mission would be wasteful, so Congress typically keeps funding it. This is the same dynamic that drove the James Webb Space Telescope from an initial estimate of around $500 million to an eventual cost of nearly $10 billion over many years of development. But there is a limit to how many times and how dramatically that strategy can work. And with Mars sample return, the gap between initial estimates and revised estimates was so large that it triggered a genuine reckoning rather than just the usual grumbling and rebaselining. The third factor is prioritization within NASA itself. NASA is not just doing Mars sample return. The agency is simultaneously running the Artemis program to return humans to the moon, operating the James Webb Space Telescope, developing the Nancy Grace Roman Space Telescope, running ongoing missions throughout the solar system, maintaining the Space Station Partnership, and working on a dizzying array of smaller science missions and technology development programs. Every dollar that goes to Mars sample return is a dollar that does not go to something else. And in a constrained budget environment, every program is fighting for its share. The planetary science community does not speak with one voice about Mars sample return. There are scientists who believe, deeply and with good justification, that bringing back Martian samples is the single most important thing we can do for planetary science in the next several decades. And there are other scientists who look at the cost and timeline of Mars sample return and argue that the same money could fund dozens of other missions to other worlds that are equally scientifically interesting and much more achievable. The tension between these views has been playing out in the scientific community for years, and it surfaces in the budget documents as competing priorities, jostling for limited resources. Let us talk about what the actual alternative architectures look like, because NASA asked for new ideas, and several genuinely interesting proposals came back. Some of them are quite creative. One approach that has attracted attention is what people have been calling a simplified or reduced scope sample return. Instead of the full mission architecture that retrieves all 20-plus sample tubes, this approach would focus on retrieving a smaller number of the highest priority samples using a simpler and cheaper mission design. The scientific return would be reduced, but so would the cost and timeline. The argument for this approach is that some Martian samples returned sooner is better than all Martian samples returned in a decade or more, or possibly never if the mission is canceled due to cost. Another approach involves the use of commercial launch providers and commercial spacecraft development to reduce costs. SpaceX's Starship, for example, has been discussed in various contexts as a potential enabler of Mars missions because of its large payload capacity and, eventually, low cost per kilogram to orbit. If a commercial provider could handle some of the transportation elements of Mars sample return, NASA might be able to focus its resources on the unique scientific and technical challenges rather than the rocket engineering. This is speculative and faces significant hurdles, but the conversation is happening. There have also been discussions about whether a different rover could help. Perseverance deposited that backup sample cache at Three Forks specifically to enable retrieval without a rover. But some mission designers have looked at whether a smaller, simpler fetch vehicle could complement or replace the role that Perseverance would otherwise play in delivering samples to a lander. Reducing the dependence on a single existing rover reduces mission risk. And there is always the possibility of international collaboration going further than it already has. China's space program has been advancing rapidly, and China has expressed ambitions for its own Mars sample return mission, with a target date that some Chinese officials have suggested could be as early as the mid-2030s. There have been tentative, careful discussions in the scientific community about whether some form of cooperation or coordination might be possible, though the geopolitical complexities of US-China space cooperation are formidable and have become more difficult in recent years rather than less. The European Space Agency has been trying to stay committed even as the American side of the program has been uncertain. ESA's Earth Return Orbiter development has continued at various levels of activity, but ESA faces its own budget constraints, and its member states have their own political pressures. The uncertainty on the NASA side has made it difficult for ESA to plan with confidence. Now here is something that does not get talked about enough in the coverage of Mars sample return delays. What is actually at stake scientifically? Not in the abstract, but specifically. What might those samples tell us? The question of life on Mars is the obvious one, and it is real. If the ancient lake environment at Jezero Crater ever hosted microbial life, that life might have left behind biosignatures, chemical traces, physical structures, isotopic ratios, organic molecules that would be recognizable as biological in origin. Finding those signatures, or definitively not finding them after exhaustive analysis, would be one of the most significant scientific results in human history. The positive result is obvious. We are not alone. Life is not unique to Earth. The cosmos is probably teeming with it. The implications cascade through philosophy, religion, our understanding of evolutionary biology, our thinking about the origin of life on Earth. Everything changes. But the negative result is also incredibly important, and this does not get said enough. If we bring back those samples and analyze them with every tool available to modern science and find absolutely no evidence of life, that is profound information. That tells us that even under favorable conditions, on a planet that was habitable for potentially hundreds of millions of years, life did not arise. That would have enormous implications for our understanding of the origin of life. It would raise the probability that life on Earth might be genuinely rare, perhaps unique. That too would reshape our understanding of our place in the universe, in a very different but equally significant way. Beyond the life question, the samples would answer fundamental questions about Martian geology. The age of the rocks, determined through radiometric dating techniques that can only be done properly in an Earth laboratory, would give us a detailed chronology of Mars's geological history. We would know exactly when volcanic activity occurred, when the climate changed, when the water disappeared. We would have a much clearer picture of why Mars became the cold, dry, radiation-blasted world it is today, when it might once have been something much more hospitable. Understanding Mars's history is also directly relevant to understanding Earth's history, because the two planets formed from the same reservoir of material in the early solar system and evolved very differently. Understanding why Mars lost its magnetic field, why it lost its atmosphere, why its water disappeared, helps scientists build models of planetary evolution that apply to Earth and to planets around other stars. There is also the question of what Martian rocks tell us about the potential for human presence on Mars. If we ever want to send people there, And there is a real conversation happening about that possibility. We need to understand the Martian environment in detail, the chemistry of the soil, the presence of perchlorates and other compounds that could be toxic to humans, the resources that might be available for in situ utilization, making rocket fuel, making oxygen, making water from local materials. The samples that Perseverance has collected would help answer all of these questions. Let us also talk about what the delay means for the broader Mars exploration program, because Mars sample return does not exist in a vacuum. It is part of a much larger strategic vision for how humanity explores Mars over the coming decades. NASA and ESA designed Mars sample return as the centerpiece of a long-term Mars exploration strategy. The idea was that returning samples would answer the big questions, guide the selection of future landing sites, provide context for interpreting the data from all the other Mars missions, and build public and political momentum for eventually sending humans to Mars. If Mars sample return gets significantly delayed or, in a worst-case scenario, canceled, that entire strategic vision needs to be reconsidered. The roadmap gets disrupted. The scientific community loses a major anchor around which future missions were being planned. There are missions currently operating at Mars or in development that are partly justified by their relationship to the sample return campaign. The continued operation of Perseverance, the Mars Reconnaissance Orbiter that is providing imaging and communications relay for the surface, ESA's Trace Gas Orbiter that has been studying the Martian atmosphere. All of these missions exist within an ecosystem built partly around the assumption that sample return was coming. A major disruption to that assumption has knock-on effects. And there is the human capital dimension. The engineers and scientists who have been working on Mars sample return for years are specialists with knowledge and experience that is genuinely difficult to replace. When programs get delayed or descoped, those people do not always wait around. They move on to other projects, other institutions, sometimes other careers. The institutional knowledge built up over years of working on a specific mission can dissipate surprisingly quickly when funding gets cut. That is a real cost that does not show up explicitly in budget documents, but is very much part of the true cost of delay. Now let us be honest about the political environment in which all of this is happening, because ignoring it would be misleading. The budget environment for federal science programs in the United States has been challenging for several years and is not obviously getting better. The debates over federal spending, the national debt, discretionary versus mandatory spending, and the priorities of different government agencies create a political context in which large, expensive, long-term science missions face real headwinds. Mars sample return is not the only program dealing with this reality. The Nancy Grace Roman Space Telescope faced its own budget battles. The Dragonfly mission to Titan, which is one of the most exciting missions currently in development, has also faced funding uncertainty. The commercial programs for lunar landing have had their complications. What is somewhat specific to Mars sample return is the combination of its scale, its cost, and the fact that the cost growth was so large and came to light in such a compressed period of time. That combination created a crisis of confidence that is proving very difficult to rebuild. Congress appropriates money based on trust, to a significant degree. Trust that agencies are giving accurate cost estimates, realistic timelines, and honest assessments of technical risk. When that trust is damaged, restoring it takes time and demonstrated performance. NASA leadership is aware of this dynamic and has been trying to respond to it. The new mission architecture studies, the calls for industry proposals, the independent reviews, all of these are partly substantive exercises in mission design and partly political exercises in demonstrating seriousness and competence to skeptical appropriators. The question is whether those efforts will be sufficient and timely enough to keep the mission alive in a form that can actually achieve its scientific goals within a time frame that matters. Let us think about what timeline would actually constitute success from a scientific standpoint. If samples are returned to Earth in 2035, Perseverance will have been sitting on Mars for 14 years, assuming it survives that long. The initial results from laboratory analysis of the samples could come within a few years of their return, so maybe by 2037 or 2038, we would have preliminary findings. The kind of truly definitive results that the scientific community is hoping for, the confirmation or denial of past life, the detailed chronology of Martian geology, the full picture of environmental history, those would take years of work at multiple laboratories around the world. Call it a decade of intensive study after return. So a 2035 sample return might yield its deepest scientific results in the mid-2040s. That is 25 years from the day Perseverance landed. If the return slips to 2040, add 5 years to everything. The deepest results might come in the late 2040s or early 2050s. Scientists who started their careers studying Mars when Perseverance landed might be approaching retirement by the time the most important results are in hand. That is the human dimension of these delays that rarely makes it into the technical documents. There is also the question of whether waiting creates risk from other directions, not scientific or technical risk, but competitive risk. China has announced ambitions for its own Mars sample return mission, Tianwen-3, with a stated target of completing sample return around 2031. Whether that timeline is achievable is genuinely uncertain. The Chinese space program has made remarkable progress in recent years, including a successful sample return from the Moon with the Chang'e 5 mission in 2020, and a successful Mars landing with Tianwen-1 in 2021. But a Mars sample return is orders of magnitude more complex than any of those achievements. Still, the possibility that China might achieve sample return before NASA and ESA has implications that go beyond science. Space exploration carries prestige and geopolitical significance that both nations are acutely aware of. Some people in the space policy community have argued that the prospect of being beaten to the first Mars sample return should be a powerful motivator for accelerating the NASA and ESA program. Whether that argument actually moves the needle in budget negotiations remains to be seen. The history of U.S. space policy suggests that competitive pressure can sometimes accelerate programs significantly, as it did during the original space race, but that it takes a particular kind of political moment to translate competitive anxiety into additional funding. What about the private sector? Can commercial space companies play a role here that goes beyond just providing rockets? This is a question that is increasingly being asked, and the answers are complex. SpaceX has been the most prominent voice arguing that commercial capabilities should be central to Mars exploration. Elon Musk has spoken openly about his goal of establishing a human presence on Mars, and Starship is designed with Mars in mind as an eventual destination. But Musk's vision is about human colonization, not scientific sample return in the traditional sense. The scientific community has largely continued to plan Mars sample return as a government mission, partly because the scientific requirements are extremely specific and demanding in ways that require deep integration between mission designers and scientists, and partly because planetary protection requirements create regulatory complications for commercial operators that are not straightforward to resolve. That said, there is growing interest in whether a more commercially engaged approach to Mars sample return might reduce costs and timeline. If commercial providers could develop some of the mission elements under contract, rather than having them built in-house at government facilities, could that change the economics? Maybe. The experience of the commercial crew and commercial cargo programs has shown that commercial development can, in some contexts, produce capable systems faster and cheaper than traditional government procurement. But those programs worked with already proven technologies in well-understood environments. Mars sample return involves unproven technologies in a very unforgiving and poorly understood environment. The risk calculus is different. Now I want to talk about something that the budget documents reveal almost by what they do not say, which is the question of mission cancellation. Nobody in official NASA communications talks about canceling Mars sample return. The language is always about restructuring, rebaselining, seeking sustainable approaches, exploring new architectures. The C word is avoided carefully and deliberately. And there are real reasons for that, not just political face-saving. Canceling Mars sample return would be a significant blow to international partnership. ESA has committed significant resources and political capital to this mission. Walking away would damage the relationship in ways that would have consequences for future collaboration across many programs. It would also be a blow to the scientific community's credibility, because the scientific case for this mission is genuinely strong, and cancellation would invite criticism that NASA cannot execute on its commitments to science. And it would create complicated questions about what happens to the samples that Perseverance has already collected and is continuing to collect. Do they just sit on Mars indefinitely? Do they eventually get picked up by some future mission that nobody is currently planning? But cancellation is not impossible, and anyone who says it definitely will not happen is not being fully honest about the situation. Missions do get canceled. The Constellation program was canceled after years of development and billions of dollars of spending. The W-1 mission went through several renamings and restructurings before eventually becoming the Roman Space Telescope. Mars Observer was lost in 1993 before it even achieved orbit. The history of space exploration is full of programs that did not make it. Mars Sample Return is a big, important, expensive mission with a strong scientific case. But being big and important and scientifically compelling does not guarantee survival in a constrained budget environment with competing political priorities. What would cancellation mean in practical terms? The sample tubes would remain on Mars, Perseverance would eventually die, and its backup cache would remain at Three Forks, preserved by the cold, dry Martian environment, potentially for centuries. Future missions, if they ever came, could in principle retrieve them. Mars preserves things quite well in some respects, but there is no guarantee that any future mission would prioritize retrieving those specific samples, especially as decades passed and new scientific priorities emerged. The scientific community would need to regroup and figure out a new path forward for understanding Mars's potential for life. That might mean investing more in situ exploration with more capable rovers. It might mean pursuing alternative mission architectures that nobody has seriously studied yet. It would mean years of replanning and arguing about priorities, all while Perseverance's legacy sat quietly in the Martian dirt. The honest truth is that even the people who work on Mars Sample Return every day, who believe in it deeply and have dedicated careers to making it happen, are uncertain about what the next 5 years of the program will look like. The uncertainty in the budget documents is real uncertainty. NASA does not currently have a finalized architecture, a locked-in cost estimate, or a committed launch date that everyone believes in. What they have is a set of ongoing studies, a continued operation of Perseverance collecting more samples, an ongoing dialogue with ESA about how to sustain the partnership, and a commitment in principle to achieving sample return eventually, under some architecture that is still being defined. That is not nothing. In fact, given where things were a year or two ago, maintaining even that level of commitment and activity is meaningful. The mission has not been canceled, the samples continue to be collected, the scientific case continues to be made, and there are genuinely smart and dedicated people working on finding a path forward that is financially and technically achievable. But it is also not the picture that the planetary science community was hoping for when Perseverance landed in 2021 and began that historic sample collection campaign. The gap between what was hoped and what is currently real is significant, and the budget documents make that gap visible in a way that press releases and program updates have not always done. Here is where I want to end, with some perspective on what this story means in the larger context of space exploration. Humanity is in a genuinely unusual moment with respect to Mars. We have a rover on the surface right now that is collecting samples we know are scientifically extraordinary. We have the technology, in principle, to retrieve those samples and bring them to Earth. We have the scientific infrastructure to analyze them in ways that could answer fundamental questions about life in the universe. And yet we are struggling to pull it all together, to align the funding, the technology, the political will, and the institutional capacity to actually make it happen in a time frame that the scientists who started working on this problem in their youth might live to see completed. This is not a story about failure. Not yet. It is a story about the genuine difficulty of doing extraordinary things and about the complicated relationship between scientific ambition and institutional reality. The Mars Sample Return mission represents some of the best of what human beings aspire to do. It is fundamentally about knowledge, about understanding our place in the universe, about answering a question that our species has been asking in one form or another since we first looked up at that red dot in the sky and wondered what it was. The delays are real, and they are frustrating, and the budget documents lay out the uncertainty in sobering detail. But the samples are there, the scientific case is as strong as it ever was. The will to make this happen, if not the immediate funding, is present in the scientific community in a way that does not simply disappear because of political headwinds. Space exploration has survived cancellations, budget cuts, political changes, and institutional crises before, and some of the most important missions in history emerged on the other side of exactly those kinds of difficult moments. The question now is whether Mars sample return can find the path through its current crisis to actually deliver on the promise that Perseverance has already half fulfilled. Whether the scientists who planned this campaign, the engineers who built the rover, the people who have dedicated careers to this mission, will get to see those sealed titanium tubes opened in an Earth laboratory and analyze what is inside them. I think they will. I think it happens. Not because the budget documents are reassuring, because they are not. Not because the timeline is under control, because it is not. But because the scientific question that drives this mission is too important, too fundamental, too deeply embedded in humanity's curiosity about its own origins and its place in the cosmos, to ultimately be defeated by budget spreadsheets and political cycles. Those forces are real and powerful, but so is the drive to answer the question. So is the knowledge that the answer is sitting right there, waiting, in those little sealed tubes in the Martian dirt. The jar is there. The question is when, and how, we are finally going to open it.